Welcome to the new section of this course introducing MLlib. Now, let's move on to the video, loading and transforming the data. Let's start with the overview of the package. At the high level, MLlib exposes three core machine learning functionalities: data preparation, feature extraction, transformation, selection, hashing of categorical features, and some natural language processing methods. Machine learning algorithms. Some popular and advanced regression, classification, and clustering algorithms are implemented. Utilities. Statistical methods such as descriptive statistics, chi-square testing, linear algebra, sparse and dense matrices and vectors, and model evaluation methods. Even though MLlib is designed with RDDs and D-streams in focus for ease of transforming the data, we will read the data and convert it to a data frame. We will first specify the schema of our dataset. Here's the highlighted code for its execute. Next, we load the data. The read.csv method can read either uncompressed or, as in our case, gzipped comma-separated values. The header parameter set to true indicates that the first row contains the header, and we use the schema to specify the correct data types. There are plenty of features in our dataset that are strings. These are mostly categorical variables that we need to somehow convert to a numeric form. We will specify our recode dictionary as show. Our goal in this chapter is to predict whether the infant alive at report is either 1 or 0. Thus, we will drop all of the features that relate to the infant and will try to predict the infant's chances of surviving only based on the features related to its mother, father, and the place of birth using this block of code. In our dataset, there are plenty of features with yes, no, unknown values. We will only code yes to 1. Everything else will be set to 0. There's also a small problem with how the number of cigarettes smoked by the mother was coded, as 0 means the mother smoked no cigarettes before or during the pregnancy. Between 1 and 97 states the actual number of cigarettes smoked. 98 indicates either 98 or more, whereas 99 identifies the unknown. We will assume the unknown is 0 and recode accordingly. So here, we will specify our recording methods. The recode method looks up the correct key from the recode dictionary given the key and returns the corrected value. The correct sig method checks when the value of the feature feet is not equal to 99, and for that situation returns the value of the feature. If the value is equal to 99, we get 0 otherwise. So we cannot use the recode function directly on a data frame. It needs to be converted to a UDF that Spark will understand. The rec integer is such a function. By passing our specified recode function and specifying the return value data type, we can use it then to encode our yes, no, unknown features. So let's get to it. First, we'll correct the features related to the number of cigarettes smoked. The withColumn method takes the name of the column as its first parameter and the transformation as the second one. In the previous cases, we do not create new columns, but reuse the same ones instead. Now, we will focus on correcting the yes, no, unknown features. We will figure out which these are with this code snippet. First, we created a list of tuples, cols, that hold column names and corresponding data types. Next, we loop through all of these and calculate distinct values of all string columns. If a Y is within the returned list, we append the column name to the YNU cols list. Data frames can transform the features in bulk while selecting features. To present the idea, consider this example. So here's what we get in return. We select the infant NICU admission column, and we pass the name of the feature to the rec integer method. We also alias the newly transformed column as infant NICU admission recode. This way, we will also confirm that our UDF works as intended. So, to transform all the YNU cols in one go, we will create a list of such transformations as shown here. Let's check if we got it correctly. Cool. Here's what we get. Looks like everything worked as we wanted it to work. So let's get to know our data better. So here we've come to the end of this video.